The second chapter of physics on the MCAT is one of the most important in the series, and it covers work and energy. So we're going to begin with a quick talk about what energy is and the different forms that it can take. This chapter deals with mechanical energy. And this can be split into two different types, and this is very, very important. So the two different types here are kinetic energy. And kinetic energy is basically the energy of motion. So any object in motion has a kinetic energy. And this has the equation half mv squared, or EK, we'll call it. So the kinetic energy is equal to half mv squared, where m is the mass of the object and v is its velocity. And energy is always measured in joules. And the other branch of mechanical energy we'll call potential energy. And the way that I like to talk about potential energy is it's the energy where an object has the potential to become in motion. So the object is currently not in motion, or the motion itself does not give it potential energy, but the object has the potential to go and move. And this will make more sense when we go into the two types of potential energy. The two types here are gravitational potential energy and spring potential energy. So with these examples, you'll see what I mean about having the potential to move. So the equation for gravitational potential energy is, I'll call this EPG. You might also see this as U sometimes, but this is equal to mgh, where m is the mass of the object, g is 9.81 meters per second squared, or the downward acceleration due to gravity, and h is the height. So the key here is the height. An object that is moved upward will have an increased gravitational potential energy. So for example, let's say that this is the ground over here and we have a box on the ground. If we were to lift this box up, I guess I should complete this box. If we were to lift that box up, right, and then we were to drop the box, it would then move downward. But at its current state, when it's raised off the ground at a height of h, the box has the potential to move downward, right? Because when we drop the box, it'll move downward. But again, when it's currently raised upward, it's not actually moving yet. It just has the potential to move. So that's called gravitational potential energy. And the other type of potential energy is spring potential energy. And I'll call this one EPS. And this equation actually looks pretty similar to the kinetic energy equation. And it's half kx squared. So the k here refers to the spring constant. And the spring constant is basically a measure of how stiff a spring is. So the stiffer a spring, the harder it'll be to compress or extend it. And the higher the spring constant, the more energy it takes to perform that motion. X is basically the displacement, or the distance by which the spring is either compressed or extended. So let me draw out a quick example here. Let's say that we have a spring over here, and I want to extend the spring. So I'm going to pull it this way, right? The spring might now look instead something like this. It's not going to be extended, and it'll look a little bit like this, right? So the spring currently, when it's being held in this extended position, is not moving. So it has no kinetic energy, but it has the potential to move, because when I drop it or I release my grip on that end, the spring is then going to bounce back and it's going to revert back to the way it looked over here. So spring potential energy is the compression or extension of a spring by the displacement of x. And we know that when we release it and it goes back to its equilibrium position or its resting position, it's going to move back to get there. So in both cases, the potential energy, whether spring or gravitational, is just the energy that gives it the ability to move, or it has the potential to move, right? Either a spring can be compressed or extended, and then when released, it'll move back, or an object can be raised and it gains gravitational potential energy, and when it's dropped, it'll move back downward. So those are the three different equations that you have to know for the different types of mechanical energy. And these are all measured once again in joules. Okay, so we've now talked about the three different forms of mechanical energy. We can rewrite this as the total mechanical energy, or the sum of the energy, and I'll write this as E total, is equal to the kinetic energy, I'll write this as EK plus EP, or the potential energy. So again, the total mechanical energy is equal to the kinetic energy plus the potential energy. And that potential energy can be in the form of either spring potential energy or gravitational potential energy. And in some cases, this total mechanical energy is conserved. But there are also some cases where we cannot assume this. So I'm going to go over those quickly. So the key difference between a system where we do conserve the mechanical energy versus a system where we don't conserve the mechanical energy is whether or not we have non-conservative forces acting on the system. So let me explain what this means, and I'm going to use a table to demonstrate this. So we have two different types of forces. We have conservative forces, and we have non-conservative forces. And some examples of conservative forces are what we just discussed. So things like gravity and springs. But examples of non-conservative forces are things like friction, heat, and air drag. Okay, so these are things that do not conserve the total mechanical energy. And in systems where things like friction are at play, then the system's actually going to be losing mechanical energy. So again, a system where only conservative forces are acting upon it will conserve the total mechanical energy, whereas a system that includes non-conservative forces is not going to conserve mechanical energy. Okay, so this is an example of a question that involves the conservation of energy, because in this question, we see that we have a 2 kilogram block that's going to slide down a frictionless ramp, which means that no energy is going to be lost to friction, which friction we said was a non-conservative force, and then we would not have been able to say that mechanical energy was conserved. But because friction is not acting upon the system, and we have no non-conservative forces acting upon the system, we can say that energy is conserved. So we have a 2 kilogram box or block that's going to slide down this ramp. Okay. And when it gets to the bottom of the ramp, it's going to compress a horizontal spring. So we've got some kind of a spring at the bottom that's kind of extended. Let's say it's like attached to a fixed point over here. And when the box slides down here, it's going to hit the spring, and the spring is going to be compressed a little bit. We know that because energy can be conserved, the initial mechanical energy, or I'll say EI, or E initial, is equal to the final mechanical energy. And for this kind of a question, and honestly any question that involves the conservation of energy, you want to identify all the different types of energy present at the start and at the end of the question. So initially, the box has potential energy because it's raised up in the air. And the gravitational potential energy, or I'll say EPG, is equal to mgh. So this is present at the start. I'll just write an I over there for initial. We have one more type of energy that's also present at the start of the question, and that is the kinetic energy, because the box initially does have movement. It's moving with an initial speed of 2 meters per second. And the kinetic energy is equal to half mv squared. Now, what about at the end of the question? I'll write an F here for final. When the box slides down the ramp and compresses the spring, we see a potential spring energy. And that has an equation of half kx squared. So I can now rewrite this as the initial energy is the gravitational potential energy plus the kinetic energy. And that's equal to the final mechanical energy, which in this case is simply the spring energy. So now we can plug in some of our values. The mass of the object is 2 kilograms. We're going to assume gravity here has an acceleration of 10 meters per second squared, and the height is 5 meters. And we're going to add that on to the kinetic energy, which is half. The mass here is 2 kilograms, and the velocity is initially 2 meters per second. And that's equal to half kx squared, or half multiplied by the spring constant, which is 200, and then x squared. So x is what we're trying to find, and that is the distance, or the displacement of the spring, how far we're going to compress the spring. And 2 times 10 times 5 is 100, plus half times 2 squared, or 4 times 2 times half is just equal to 4. And that's equal to half times 200 times x squared. So it's equal to 100 x squared. Then when we add this up over here and then divide both sides by 100, we get x squared is equal to 104 over 100. And that's basically just 1. So this is like an example of how we can kind of estimate on the MCAT. Here we have x squared is basically equal to 1. And then when we square root that to solve for x, we get x is roughly equal to 1 meter. Or essentially, after all this, we know that when our box over here slides down the ramp and it compresses the spring is going to be compressed such that the displacement is 1 meter. I know I've kind of said this in my last two videos as well, but if any of the math here isn't clear, please let me know in the comment section and I'll be happy to make a video or maybe a short series about how to approach the math on the MCAT. Now we're going to kind of move on to the next half of this chapter, and we're going to be discussing work. So work is basically how we transfer energy. It's not energy itself, but rather the difference in energy, or the process of moving energy into or out of a system. And we can do either positive work on a system or we can do negative work on a system. And an easy way to tell the difference between these two is that if a system gains energy, then we have done positive work. And an example of this can be lifting a box. So if you have a box on the ground here, for example, and we raise it up, this box has now gained gravitational potential energy, right? So the box or the system gained energy. In this case, again, gravitational potential energy. So lifting the object caused the system to gain energy, which means that we did positive work. And the opposite of that is where a system would lose energy. And do you remember how we talked about conservative and non-conservative forces? We said that non-conservative forces are one where the energy is not conserved, right? Or one where a system is likely to lose energy. So for example, friction does negative work on a system because friction will cause the system to lose energy. If we have, for example, an object that's sliding on the ground, right? It currently has kinetic energy, right? Because it's in motion. But as it moves, it's going to eventually slow down and lose that speed because of friction. So friction is causing the system to lose energy, and in this case, lose kinetic energy. And we measure work in joules, just like we do for energy, because work is, again, just the difference in energy, the transfer of energy. And the first equation that we're going to cover for work is work is equal to force times displacement multiplied by cosine theta. And what's important here for now is just F times D, or force times distance. And it's basically the force that we apply across a certain distance is equal to the work. So if we push a box over here, and let's say we push this box with 5 newtons of force, and this moves across a distance of 10 meters, then the work done here is going to be 50 joules of energy. Okay, and now I'm going to talk briefly about what the cosine theta portion of this means. And the key here is that only the forces that are acting in the same direction as the motion actually do work. So in this case, the box is going to be sliding this way, right? So that's the direction of motion. So only forces that are parallel to this are actually going to do motion. And in this case, the force is completely parallel, or the cosine theta is just equal to 1. So the full force is going to be contributing to that work. But if this force was applied at an angle, like let's say it was applied at an angle like this, it's pushing the box downward and to the right. Only the horizontal component of this force is actually doing work. That's why we have to do cosine theta of this force. So just to show this in a bit of a bigger illustration, if we're pushing downward and to the right, we can break this down into its vertical and its horizontal components. Okay? And this over here is the force multiplied by cosine theta, and this is the force multiplied by sine theta. And once again, any questions about the math, let me know in the comments. But only the component of the force that is parallel to the motion, which is to the right side, only that component of the force is actually doing work. So that's why we have to add the cosine theta segment of this equation as well. So one more thing that we can note from this are actually the units that are being used. We know that force is measured in newtons, and distance or displacement is measured in meters, and work is in joules because it's just the difference in energy, right? So this tells us that joules or energy is actually equal to Newton meters. Okay, so that's the equation for work that's done by forces. But one other common type of work is one that involves gases, and this is called thermodynamic work. So in this case, work is equal to pressure, which usually stays constant, multiplied by the change in volume. So in this case, when the gas expands or gains volume, so you can actually think about this, for example, a balloon, right? If you have a balloon over here and it's going to blow up, we're going to, blow some air into there and the balloon's going to expand, right? This gas has now gained volume. So because the volume is gained, we have done positive work on the balloon. All right, so pressure times volume is equal to thermodynamic work. And one example of this, or one way that this could be shown, is actually through a graph, right? So if we have, let's say, a pressure volume graph. So we can put pressure over here and volume over here. And let's say that the graph looks a bit like this. Remember how in the first video I said that the area beneath the curve, or in this case, the area beneath the line, is equal to the y-axis multiplied by the x-axis? So here, the y-axis, or pressure, multiplied by the x-axis, or the volume, is actually equal to work. So if you get a pressure volume graph, then the area below the curve, or below the line in this case, is equal to the work done by the system, or on the system. Now we're going to talk about one more concept involving work, and that is power. So this one's pretty simple. Power is just the work done divided by time. So it's just how fast we're doing work. And power is measured in watts, right? And we know that because work is measured in joules, and the SI units for time are seconds, then watts are just equal to joules per second, right? And again, it's just how much energy we're using per second. And the work here can be, in a few different ways. We could have work as force times displacement. We could have work as pressure times the change in volume. But in any case, we divide the work by the amount of time that it took to do that work, and we get the power in watts. Okay, the last main concept that I want to cover is mechanical advantage. And this is a bit of an application of what we've already talked about. But mechanical advantage, and I'll use the symbol or the notation MA here, is equal to the output force divided by the input force. So essentially, mechanical advantage is just the ratio between the force that we put in and the force that we actually get out of it. So what's important here, though, is that the work is still conserved. So the amount of energy that we put in is still going to be the amount of energy that we get out of it, or the work that we put in is going to be the work that we get out of it. But the force can be increased. And if we have a mechanical advantage of greater than 1, then it means that the output force is greater than the input force. So because the work itself is conserved and work is equal to force times distance, then the product of those two variables must be constant. So this is going to be conserved. But how can we increase the force that we're getting out of it while putting in the same amount of work? I'm going to use an example to have this make a lot more sense. And the example that I'll use is a classic example of a system that provides a mechanical advantage, and that is a ramp. Let me draw this a little bit straighter. So a ramp provides a mechanical advantage compared to just lifting something straight upward. So let's say we have a box, and we can either lift the box straight upward, a distance of 5 meters, and to lift the box straight upward, it takes a force of 10 newtons. The alternative might be something like a ramp. Let's say that to slide a box up a ramp, it only requires 5 newtons of force. But the distance here is 10 meters. So we're going to have to slide it a further distance, a distance of 10 meters, but we only have to apply 5 newtons of force. So the work in the first example was equal to 10 newtons, the force, multiplied by 5 meters. And that gave us 50 joules of work. So it took 50 joules to raise the box up. And in the second example, it was the same thing, right? Work is equal to 10 times 5. But in this case, it's 10 meters times 5 newtons. And that's equal to, again, 50 joules. So these two examples were the same in that it took the same amount of work to raise the box up 5 meters. But the difference is that in the second example, we increased the distance across which the force was applied. So the distance was increased. And as a result, because the work stayed the same, the force decreased. So we're doing the same amount of work, we're getting the same result, but because we increase the distance, we can actually lower the force required. Okay, now let's apply that to pulleys. And pulleys are something that people tend to have a very hard time with, but I'm going to show you a way to make that a lot easier. Okay, so we know that, again, mechanical advantage is equal to the output force divided by the input force. Okay, so with pulleys, what I would say is that the mechanical advantage is just equal to the number of supporting ropes. And this will make more sense once we look at a visual. Okay, so this is a classic two-pulley system. And essentially what's happening here is that you're applying a force onto one rope, right? This rope over here, you're pulling downward. And then it's going to cause the block to be lifted by two supporting ropes, right? Those two ropes over there are both going to pull the block. And here what's happening is that because there's two ropes that are going to lift up the block, you only need to apply half the force and it'll be acting upon twice as much rope. Okay? So this is kind of, so this is basically the same thing as what we just described, where work is equal to force times distance. And here the distance is essentially doubled because there's twice the amount of rope, right? There's two ropes supporting that one block. So if the distance is doubled, we have 2d, then for the work to be the same, we're going to have half the force applied, or 0.5 F. So essentially in a two-pulley system, you only have to put in half the force to get the same results. But honestly, the reason I say that pulleys can be solved in a much simpler way is that the mechanical advantage of a pulley is always equal to the number of supporting ropes. Here we see that the block is supported by two ropes, right? There's two ropes that are carrying the block. So all that you really have to do is know that the mechanical advantage, which is equal to the output force over the input force, is equal to 2. Or the force that you put in is only going to be half as much as the output force. So the force that we're going to get out of it, which is going to lift the block upward, is double what we're putting in. It's that simple. And finally, we're going to deal with an equation that's pretty similar, and this is called efficiency. But in this case, we're not dealing with the force, we're dealing with the work. So energy is not always fully efficient, right? Because as we've mentioned, there's some non-conservative forces, things like heat, friction. So the efficiency of a system is equal to the work output divided by the work input. So exact same equations before, but now we're dealing with the work and not the forces. And usually the way that this is going to be written is as a percentage. So you're going to times this by 100%. So for example, if you put in 100 joules of energy, that would be the input energy. And we only get 90 joules out of it. That's the output energy. Then the efficiency of the system is equal to the output energy, or 90 joules, divided by the input energy of 100 joules, or 0.9. And we're going to multiply that by 100%, which gives us a 90% efficient system. And what's important to note is that the efficiency is never going to surpass 100%, right? We're never going to have a system that's more than 100% efficient. Whereas when we're talking about forces and the mechanical advantage, a system with a mechanical advantage actually lets us have a greater output force than the force that we put in. But when it comes to efficiency or the energy of the system, we're never going to be able to get more work out of a system than we put into it. So the maximum efficiency that you can see is 100% efficiency. As always, here's a list of all the equations that we've covered this chapter. There are quite a few, but as I mentioned before, I've been working on a comprehensive physics equation sheet for this test, and I have finished that. And I also made a couple worksheets where basically half of every equation is omitted. So it gives you a chance to work through all the equations yourself and fill in the blanks and really test your understanding and memorization of those equations. So If you'd like a copy, just send me an email. I have my email down below in the description. And I'll see you guys all next time.